As software applications grow and evolve, new requirements and features are constantly introduced. Without a proper design foundation, even a small change in one part of the codebase can unexpectedly break another, leading to bugs and frustration. This is where the solid principles come into play. These 5 guidelines help developers create code that is easier to maintain, extend, and understand. In this video, we'll explore each solid principle, why it exists, and how it can transform your approach to software design. Imagine you're working on a large application. A simple change in one module unexpectedly causes failures in another. This happens because responsibilities are tangled together, making the code fragile and hard to modify. Developers often face this challenge, especially as projects scale. The solid principles were created to address these issues, providing a structured approach to writing robust and adaptable code. Let's start by understanding the first principle, single responsibility. Single responsibility principle, or SRP, states that a class should have only one reason to change. This means each class should focus on a single responsibility or job. When a class takes on multiple roles, changes in one area can inadvertently affect others. By isolating responsibilities, SRP makes code easier to maintain and less prone to bugs. Let's see how this works in practice with a common example. Consider an order service class that not only creates orders, but also sends emails and generates reports. If a developer modifies the email logic and accidentally breaks order creation, it's because these responsibilities are coupled together. This makes the code fragile and difficult to manage. By separating these concerns into different classes, each with its own responsibility, we reduce the risk of unintended side effects. SRP exists to isolate changes. When each class has a single responsibility, changes in one area don't ripple through the entire system. This makes the codebase more resilient and easier to understand. Developers can confidently update one part of the application without worrying about unexpected consequences elsewhere. Next, let's move on to the open-closed principle. The open-closed principle, or OCP, suggests that software entities should be open for extension, but closed for modification. In other words, you should be able to add new functionality without changing existing code. This principle helps prevent bugs and makes it easier to introduce new features. Let's look at a practical example involving payment systems. Imagine you have a payment system that initially supports only card payments. As your application grows, you need to add support for UPI, wallet, and crypto payments. A common approach is to add more if-else statements to the existing class. However, this means modifying the same class every time a new payment method is introduced, which can lead to errors and make the code harder to maintain. OCP exists so that new functionality can be added through new classes, rather than by modifying existing code. This approach keeps the original code stable and reduces the risk of introducing bugs. By designing your system to be easily extendable, you make it more adaptable to future requirements. Now, let's explore the Liskov substitution principle. The Liskov substitution principle, or LSP, states that a child class should be usable wherever its parent class is expected. This ensures that inheritance models a true behavioral relationship. If a subclass cannot fulfill the contract of its parent, it can cause unexpected failures in the code. Let's see how this plays out with a simple bird example. Suppose you have a bird class with a fly method. A sparrow class can fly, but a penguin cannot. If penguin extends bird and throws an exception when fly is called, code that works with bird will fail when used with penguin. This violates LSP, as the subclass does not behave like its parent. Proper inheritance should always maintain the expected behavior. LSP exists to ensure that inheritance represents a relationship. When subclasses conform to the expectations set by their parent classes, code becomes more reliable and predictable. Violating LSP can lead to subtle bugs and confusion, especially in large codebases. Next, let's discuss the interface segregation principle. The interface segregation principle, or ISP, states that clients should not be forced to depend on methods they do not use. This means interfaces should be small and focused, rather than large and general. By splitting interfaces, you allow classes to implement only what they need. Let's see how this applies to our bird example. If you create a bird interface with both fly and swim methods, all birds must implement both, even if it doesn't make sense. Sparrows would need to implement swim, and penguins would need to implement fly, leading to unnecessary or empty methods. By splitting the interface into smaller, more specific ones, each class only implements what's relevant to it. ISP exists to encourage smaller, more focused interfaces. This makes your code easier to maintain and understand, as each class only deals with the methods it actually needs. It also reduces the risk of errors from unimplemented or irrelevant methods. Now, let's move on to the final solid principle, dependency inversion. The dependency inversion principle, or DIP, states that high-level modules should not depend on low-level modules. Instead, both should depend on abstractions. This decouples your code and makes it more flexible. By relying on abstractions, you can easily swap out implementations without affecting the rest of your system. Traditionally, an order service might directly depend on a card payment class. This creates a tight coupling between the two, making it hard to add new payment methods or change existing ones. By introducing a payment service abstraction, order service can depend on the abstraction, and different payment methods can be implemented independently. DIP exists to promote flexibility and scalability in your code. By depending on abstractions instead of concrete implementations, you can easily extend or modify your system without breaking existing functionality. This principle is especially valuable in large, complex applications where change is constant. Applying the solid principles in your daily development can seem challenging at first. However, with practice, these guidelines become second nature. They help you write code that is not only functional but also clean, maintainable, and ready for future changes. Let's review how each principle contributes to better software design. The single responsibility principle ensures that each class has one job. This isolation of responsibilities makes your code easier to test, debug, and extend. When changes are needed, you know exactly where to make them, reducing the risk of unintended side effects. The open-closed principle allows you to add new features without modifying existing code. By designing your system to be easily extendable, you make it more robust and less prone to errors. This principle is key to building scalable and adaptable software. The Liskov substitution principle ensures that subclasses can stand in for their parent classes without causing problems. This keeps your inheritance hierarchies logical and predictable, making your codebase easier to understand and maintain. The interface segregation principle encourages you to create small, focused interfaces. This reduces complexity and ensures that classes only implement what they need. The result is cleaner, more maintainable code with fewer unnecessary dependencies. The dependency inversion principle decouples high-level and low-level modules by introducing abstractions. This makes your code more flexible and easier to extend. You can swap out implementations without affecting the rest of your system, making future changes smoother. Code that follows solid principles is naturally easier to test. With responsibilities separated and dependencies abstracted, you can write focused unit tests and catch bugs early. This leads to higher quality software and more reliable releases. As your application grows, solid principles help ensure that your codebase remains manageable. You can add new features and scale your system without fear of breaking existing functionality. This is crucial for long-term project success. To sum up, the solid principles provide a powerful foundation for writing clean, maintainable, and scalable code. By applying single responsibility, open-closed, Liskov substitution, interface segregation, and dependency inversion, you can tackle complexity with confidence. Start small, practice consistently, and watch your code quality soar.